Namaskara. We are continuing our discussions on all pair shortest path problems. We have seen two algorithms which are based on the Bellman equations for bounded path lengths, and when we map that equation to something similar to matrix multiplication, we got a more efficient algorithm. We are going to see somewhat similar algorithm, but this is going to be based on a slightly different approach. The algorithms that we have described earlier are based on the last edge of the shortest path. Okay. So, considering the last edge and the remaining edges of the shortest path, we derived the recurrence equations. Now we are going to generalize it for an arbitrary intermediate node. So you can say in this picture a path from I to j, and k is an intermediate vertex, arbitrary intermediate vertex. It could be anywhere in the path, it need not be the last edge. Okay. If k is an intermediate vertex in a shortest path from I to j, the portion of the p from I to k as well as the portion of the path from k to j, they are all shortest paths. So let us assume that this is the shortest path. This part is a shortest path, and again this part is also a shortest path. Okay. For any intermediate vertex, both these parts are shortest path. This part, the portion of the path, so the whole thing is called p from I to j. P from I to j is written as p from I to k plus p from k to j equals p I j. You are, with respect to an intermediate vertex, we are split into two parts. The claim is this part is the shortest path and this part is also a shortest path. Not only this, we have a kind of a converse for this. By combining shortest paths in some careful manner, we will be able to get bigger shortest path. It is a kind of converse for that. Okay. Suppose qik is the shortest path from I to k, and let us assume that it has got at most L edges, and rkj with the shortest path from k to j with at most L edges. Okay. So you have. Now let us combine for various k, right. K is an arbitrary intermediate vertex and k can be any vertex other than I and j. So let wikj be the walk obtained by concatenating qik and rkj. Okay, notice that I am using the word walk. Okay. When two paths are concatenated, it could be like this. This might be a path from I to k, this might be a path from k to j, right. That means you see that when you combine them, there is repetition and other things possible. Only when they are vertex disjoint, they get connected like this and you get a path. If the paths are vertex disjoint and if they are attached at one end, the whole thing will be a path. If the paths are not vertex disjoint, when you combine them, you get a walk. So let wijk be the walk obtained by concatenating qik and rkj. So let pij be the shortest walk among all these things, okay, the shortest one. Then pij is a path, pij is the shortest path from I to j with less than or equal to 2L edges. Remember, G is a graph that has got no negative cycle, no zero cycle. So if a walk has a cycle, if a walk has a cycle, this cycle can be simply knocked out and you will get a shorter one. Therefore, the shortest walk will always be a path. If a walk has got a cycle, the edges and vertices in that cycle can be removed and the repetition can be reduced. In this way, all repetitions can be removed. That means you are going to get a path. This is true only for the graph that has got no negative cycle or zero cycle. Our graph has that property. That is the reason why anything that is shortest, that will be a path, okay. And the total length will be 2L. Why it is 2L? You have a path of length L and another path of length L. Together there will be 2L edges. So it is a walk of maximum size 2L. It will have maximum 2L edges and this is the shortest among that. That is the reason why it will be a shortest, it will be a path, and the upper bound for the number of edges will be 2L, okay. So this is what the picture like, combining Q and R. The first claim is that if K is an intermediate vertex, then the portion from I to K will be the shortest one. Suppose this is not the shortest, the part of Q, the part of the P, namely Q from I to K, that is not the shortest. Consider the shortest path, same kind of an argument, okay. Q dash, I do not know, again it is causing some problem. This is Q dash. Q dash is the shortest path, therefore weight of Q dash will be less than weight of Q. Now Q dash plus R may be a walk. Every walk has a sub-walk which is a path and its weight will be less than or equal to weight of the walk. This is a standard property in a graph that has got no negative cycle. If a walk has a cycle, I can knock the cycle and get a shorter walk, and in this way I can keep knocking all the cycles. I can get a sub walk which is in fact a path, and weight of that path will be less than or equal to weight of the walk. The reason is everything that I has knocked out is positive, all cycles are positive, no negative or zero cycles. So when you knock a positive cycle out, the weight reduces. So Q plus may be a walk and it has a path P dash such that weight of P dash is less than weight of Q dash plus R. It has a path which has this property less than or equal to, okay. If the walk itself is a path, it will be equal. If the walk has cycles, you are going to remove the cycles and get a path with a smaller weight, therefore smaller than or equal to this. Now you can see that weight of P dash which is less than or equal to weight of Q dash plus R which is less than or equal to weight of q dash plus weight of r, which is less than weight of q plus weight of r. Weight of q plus weight of r is equal to weight of p. That means weight of p dash is less than weight of p. This contradicts the minimality of p. This contradicts, p is the shortest path. Now I have found out another path from I to j which has smaller weight. That is not possible. You cannot have something smaller than the shortest. So this contradicts the minimality. Therefore such a q dash cannot exist. Hence such a q dash cannot exist, which implies q is a shortest path. Similarly, r is a shortest path. Therefore, if you take a path p from I to j and split the shortest path at any point, any intermediate point, these portions will be shortest paths. Therefore, the shortest path from I to j is a combination of shortest path from I to k and k to j. You do not know for which k this is true, right. We do not know the path yet. I know that the path has that property. It is a combination of two shortest paths from I to k and k to j, but I do not know k. So what I do is I do the combination for every k and take the minimum, right. So the natural way to, when you do not know, exhaustively search. I do not know the k, so for every k I compute this. I can compute, note that these are the shortest paths with smaller bound. If p has length L, all these things will have length less than L. In fact, what we have seen is, by the way of combining, the upper bound is 2L, right. So here is the dij to L, dij to L is minimum of dlik plus dlkj. There is a shortest path with upper bound on edges with L. So this is less than or equal to L, I to k. This is less than or equal to L, k to j. This is less than or equal to L, this is less than or equal to L. The whole will be less than or equal to 2L. So something on the notation I would like to discuss now. The notation with parenthesis in the top defines a sequence of matrices. So D1, D2, that defines a sequence of matrices. The notation of a matrix without the parenthesis is the power of the matrix. For example, W times W times W is W cube. This is a matrix multiplication done twice, in other words W cube. And if you take W square dot W square, it will be W4. So when I write a number without parenthesis, it represents the exponent or the power of the matrix. But when I put a parenthesis, it defines a sequence of matrices. So, I want to have a sequence of matrices, and the sequence of matrices is denoted by D1, D2 and Dn and so on. Here D2L is given as a combination of these two, and this combination shows that it is like a matrix multiplication. We have already seen min and plus. Min would be converted to sigma, plus will be converted to dot. It will look identical to a matrix multiplication operation. Therefore, D of 2L can be written as D of L square. Okay. So, we must add a parameter D of 2L. Therefore, just by keep squaring you are going to get higher and higher powered values in the sequence. So, you do not have to compute D1, D2, D3 and so on. From D1 you can go to D2, from D2 by squaring you can go to D4, from D4 by squaring you can go to D8 and so on. So, I can always go higher value because I know that the shortest path, not only that, any path cannot have more than n minus 1 edges. Therefore, D of n minus 1 is equal to D of L for all L greater than or equal to L minus 1, the same thing that we did earlier. All higher powers are same. So, I can go to the nearest higher power, which is a power of 2, because in the doubling process I get a power of 2. The same illustration you can recall, the way in which I would compute D13 is, I know that D13 is D16. D16 can be easily computed as D1 to D2 to D4 to D8 to D16. It is easy to compute. So, I will compute D13 by computing D16 easily. So, maximum I am going to have log n steps, because 2 power log n will be greater than n minus 1. So, by stepping, by squaring log n times, I get the answer. So, I start from D equal to W. Notice that I am not starting at D equal to D0 as I did in the previous algorithm. I am starting at D equals D1. D1 is nothing but W. So, D is W. Then I keep squaring it and I return D after log n iterations. That is it, and the problem is solved. It is solved in a different way. We are now considering the intermediate vertex, and based on that approach we have got another n cube log n algorithm. The complexity is again n cube log n. The reason is I am doing log n times the squaring. Each squaring is a matrix multiplication. A matrix multiplication costs n cube steps. Log n matrix multiplications, they would cost log n cube step. This algorithm is due to Fisher and Mayer. For the all pair shortest path problem, we have seen an n power 4 algorithm and 2 n cube log n algorithm. We are going to discuss about another algorithm whose complexity is order n cube, and it is based on an ingenious and an out of the box thinking. We will introduce the notion of k paths and then discuss the algorithm by Floyd and Warshall whose complexity is order n cube. Then we conclude the discussions on all pair shortest path problem by discussing Johnson's algorithm, which is just a very clever combination of Dijkstra's algorithm and Bellman and Ford algorithm to achieve further efficiency on sparse graphs. Okay. So, this algorithm is going to be based on a different formulation on the intermediate vertex. There are several researchers who have worked on this idea, and more or less at the same window of time several algorithms based on this idea have been published. Okay. Call a path from I to j is a k path from I to j if all intermediate nodes are less than or equal to k. That is, the path from I to j pass through the set of vertices 1 through k. Only these vertices are there. So, every k path is automatically an L path for all L greater than k. If I have a 20 path, it is automatically a 21 path, 27 path, 43 path and so on. Because all intermediate vertices are less than or equal to 20 means they are less than or equal to 25, they are less than or equal to 43 and so on. So, any k path is automatically an L path for all L greater than k. So, what is a 0 path? 0 path is just an edge I to j if it exists, no intermediate vertex. So, I to j no intermediate vertex means it is a path with no intermediate vertex, it is an edge. Therefore, 0 path is nothing but an edge. Note that the k is independent of I and j. Nodes I and j are source and destination vertices. The upper bound on k is applicable only for the intermediate nodes, not for the n nodes. N nodes and k are independent. Okay. For example, I can have 15, it can go via 7, 12, 8. This is a 12 path connecting 15 and 20. Suppose instead of 8 it is 18. It is an 18 path because all intermediate nodes are less than or equal to 18. You can see that the k path, the k value can be smaller than both and it can be larger than both. It can be an in between value. K is an independent value. So, let delta k ij be the weight of the shortest k path from I to j. Since n is the largest vertex label, you have vertex v is defined from 1 to n. So, all the intermediate vertices are obviously less than or equal to n. The largest value an intermediate vertex can have is n. Therefore, delta n ij equal to delta ij for all ij, okay, because n is the last, this is n. Let me write down that delta n ij is equal to delta n ij is equal to delta ij, because delta n ij is the shortest among all paths. All paths are included in this set. Therefore, delta n ij is, therefore delta n ij is the value that we are looking for. Our approach is same. I want delta n ij if I know delta k minus 1 ij for all I and j. Can I use this to compute delta k ij for all ij? Is it possible for me to do this? Okay. If it is possible to do that, then I will start from delta 0 ij, keep applying that process again and again and reach delta n, right. From delta 0 I go to delta 1 for all ij, and from delta 1 I go to delta 2 and I stop it when I get delta n. The standard approach. Okay. I know delta 0 ij, delta 0 ij is wij, because if an edge exists, that is the path and its weight is the weight of the shortest path. If it does not exist, it is infinity, and that is there in wij. Therefore, delta 0 ij is wij, and I am going to define a power k is given by delta k ij, right. Now, a k path from I to j may contain k or may not contain k. If it does not contain k, all its intermediate vertices are less than or equal to k minus 1, and hence it is in fact a k minus 1 path, right. So, consider this path I to j, k is not there, all of them are less than or equal to k and k is not there, therefore, all of them are less than or equal to k minus 1. Since all of them are less than or equal to k minus 1, it is a k minus 1 path. Therefore, delta k ij could be the minimum in this, which is the delta k minus 1. Therefore, this is one possibility. If the k path contains k, that is the second case. If it contains k, here is the picture for them. The k path contains k. Therefore, this part does not have k. It does not have k, it is all less than or equal to k, therefore, it is less than or equal to k minus 1. Same is the argument for that. We know that if k is an intermediate vertex, this condition is true and they are the shortest path. Therefore, delta k ij equal to delta k minus 1 ik, this is delta k minus 1 ik plus delta k minus 1 kj. This is the length of the shortest path and this is the length of the second shortest path. They are combined and then you. So, this is the case if k is there. We do not know whether it is there or not. So, what we do is that we find the minimum of these two. This is the case when k is not there, this is the case when k is there. The minimum of these two take care of all possibilities. Therefore, delta k ij is computed from delta k minus 1 matrix. So, in the delta k minus 1 matrix, what are the entities you look at? Delta k minus 1 ij. Okay. So, here delta k minus 1 matrix, delta k matrix. In delta k matrix, I want to compute this. If I want to compute that, what is that I have to do? I have to look at this value, the same ij value, ik and kj, ik and kj depending on where k is. Let us say ik, k is less than j, let us say, then ik will be somewhere here, kj will be somewhere here, ik and kj. So, just look at these three values, that is all. We are not going to look at anything else. So, to compute delta ik, one addition and one comparison, that is it. So, you can see how one matrix is generated from the previous matrix exactly in square steps. n square addition, n square comparisons, because per element one addition and one comparison, one addition and one comparison to evaluate one element. There are n square element, therefore n square additions and n square comparisons. You can see, therefore this process for each hop n square and n square and n square, each hop is n square, there are n such hops, therefore the total complexity is n cube. So with n cube steps we were able to solve the problem. It is an amazingly clever solution, right. Our previous solutions were all either n power 4 or n cube log n. Here, by looking at the collection of shortest path from the maximum value of the intermediate one and not the lengths, we got a formulation, and for this formulation the time it takes to go from one matrix to the next matrix is only n square. Therefore, I can pass through all the steps in n cube time. Amazingly clever and simple algorithm. So here is the algorithm Floyd-Warshall. For k equal to 1 to n, I have to compute ak using ak minus 1, that is I compute a1 using a0, I compute a2 using a1, I compute a3 using a2, I similarly compute an. How do I do that? How do I go from one to the next? If I want to compute kth element, I have to consult k minus 1 element and then get the job done. Okay. So each is taking one comparison and one addition, therefore the total complexity is n cube. Very simple algorithm, stunningly simple algorithm, and this is called Warshall's algorithm, and the complexity is n cube. The problem with Warshall's algorithm is whether the graph is dense or sparse, the complexity is always n cube. Okay. Suppose the graph is a sparse graph like planar graphs or any sparse graph. Is there a way I can reduce the complexity further, because that graph, the vertices are same but the number of edges are small. The number of edges can vary. For example, if you have 1000 vertices, the number of edges could be as high as 500,000, right. But it could be even 5000, 6000, it's the same order as the number of vertices. If it is sparse, is there a way I can take the advantage of the smallness of the edge set and arrive at a more efficient solution? In the worst case it will be the same. For the dense graph the complexity will be same, but for sparse graph we may take an advantage of the sparsity and may arrive at a clever solution, and that is what is done by Johnson's algorithm. This completes the discussions on Floyd-Warshall's algorithms. Thank you.